Okay, so it's time to go over the final two problems, right? I'm going to try to do them fast because, again, the last few videos have been so long that I'd rather just make this one as quick as possible. So this one threw me a little bit. I did get the answer originally, but now I can't remember how I did it. But so basically what you want to do, so it says the interior of a quadrilateral is bounded by the graphs of x plus ay squared equals 4a squared and ax minus y squared equals a squared, where a is a positive real number. What is the area of the region in terms of a valid for all positive a? All right, well, I think first we want to have some idea of what these should look like, right? So if we start with x plus ay squared equals 4a squared. Now, if we square root both sides, we would have x plus ay equals 2a, or x plus ay equals negative 2a, right? It can be plus or minus. Right? So that gives us two lines. And then what about ax minus y squared equals a squared? Well, square root that, you get ax minus y equals a, or ax minus y equals negative a, right? So we have four lines. If we could somehow maybe simplify them a little bit more to have them maybe in the form y equals, right? That would definitely help to understand what these look like. So if you do that, you end up getting the following. You get y equals, so what we get? For the first one, we get y would equal negative 1 over ax plus 2, right? For the, sorry. For the second one, we would get y equals negative 1 over ax minus 2. For the third one, we would get y equals ax plus a. And for the fourth one, we would get y equals oh no, sorry, you get y. Well, for the third one, you would get y equals ax minus a, right? For the fourth one, you get y equals ax plus a. So now, probably the easiest way to solve this problem is to just pick a number for a, right? And what's the easiest possible number that we could pick for a? Right, the easiest number you could pick for a would be 2. If we pick 1, several of the answer choices end up being equal. So instead, I would probably pick 2 for a, right? And let's graph what these lines look like. So if we graph, now notice how these lines are perpendicular, right? These two lines are perpendicular to these two lines, right? Because their slopes are opposite reciprocals. So, and notice how by plugging in 2, right, this will, right? So basically we're graphing y equals negative 1/2 x plus 2, which is going to kind of go like this, right? Then we're going to graph y equals negative 1/2 x minus 2. Then we're going to graph y equals 2x plus 2, which is going to be perpendicular and go through that same y-intercept, right? And then we're going to graph y equals 2x minus 2, which is going to kind of go like this, right? I don't think they meet on the axis, if I'm mistaken, because it would be y equals 0, because they don't have the same, yeah, so they're not supposed to meet at the axis, but, so this is negative 2, right? And this is y equals 2x plus 2. This would be y equals 2x minus 2. This would be y equals negative 1/2 x plus 2. And this would be y equals negative 1/2 x minus 2, right? So now we want to find the area of this. And remember, this is a rectangle, right? So, and it's definitely symmetric about the origin, right? So if we can find the area of this triangle here, right, then we can just multiply it by 2. So if we, all we just need to do is get the area of that triangle. But notice how we know that the base of the triangle is 4, right? That distance is 4. So then we just need the height. But the height of the triangle going this way is basically going to be the x value where these two lines intersect, right? So we can find the x intersection of those two lines. So that's going to be 2x plus 2 equals negative 1/2 x plus 2. Minus 2, sorry, minus 2. So by solving that, we would get 4 equals 5/2 x, right? X equals 8/5, right? So the height is 8/5. So the area of the triangle would be 1/2 4 times 8/5. But the parallelogram or the rectangle will be 2 times that. So get rid of the half. So it's just going to be 4 times 8/5, which is 32/5. So if we can just find an answer choice that equals 32/5, we're done, right? So plug in 2 to A, right? We're going to get 8 times 4, 32 over 3 squared, 9. So that's wrong, right? This one is not going to give you 32 on top. This one's going to give you 16 over 3. No. This one will give us 8 times 4 over 5, 32 over 5. Okay, so there's our answer, right? This is not the answer. And then E would give us 16 over 5. So that's wrong. So the answer is D, right? So the answer for number 24 is D. And all we did was using the answer choices, was picking a number, right? Which is a very valid strategy when you have multiple choice answers. All right, last but not least, 25, which, believe it or not, I don't think is the hardest question for all of them, right? It's actually not as bad as you would think. You do have to do a certain amount of like casework, which, I'm simplifying a lot, but, obviously it took me kind of a while because you have to consider all the possible cases. How many ways are there to place 3 indistinguishable red chips, 3 indistinguishable blue chips, and 3 indistinguishable green chips in the squares of a 3x3 grid so that no 2 chips of the same color are directly adjacent to each other, either vertically or horizontally? So we're trying to place 3 red, 3 blue, 3 green chips into a 3x3 grid in such a way that no 2 chips that are directly next to each other, horizontal or vertical, are going to be the same color, right? We need to know how many ways is that possible. All right, so I'm going to use the whiteboard and kind of let you know. Okay, so the key thing with this question, so obviously for you to kind of sit and try to calculate every possible thing is really just not going to work because you're just going to get too flustered and you're not going to remember what you already did. You have to be very, 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 very systematic about how you handle this, right? You need to do it in a way where you're sort of building the possible patterns, right? Okay. So let's start by putting something in the top left box, right? And we can obviously pick any of 3 possible colors. But let's just say without loss of generality that we decide to put a green chip in the top left corner, right? And then now what I'm going to do is I'm going to split into 2 cases. One in which these 2 are the same color, and then later on I'm going to look at the case where these 2 are different colors. And by these 2 I mean left middle and top middle, right? So I'm going to start with the case where those 2 would be the same. Oh, sorry, that doesn't look very nice. I'm going to start with the case where those 2 would be the same color, okay? And obviously we have 2 colors to choose from, red or blue in this case. So I'm going to multiply by 2, right, to indicate that there's 2 possible colors that I can pick to put in those spots. So let's just say again, without loss of generality, that we pick red. So I'm going to decide to put red in those 2 spaces, right? Now, I have a couple of different situations to test out to see if they can work, right? And the way that I set this up was I looked at this diagonal, right? This diagonal here, and looked at some different possible patterns that might be possible, might not be possible, right? So one would be where the bottom left and middle ones are the same color and the top right one is a different color, right? And then another case would be where the middle and top right are same color and bottom one is a different color, right? Then I considered a case where potentially maybe they're all the same color. And then I looked at a case where the top right and bottom left are the same and the middle one's a different color, right? And then I looked at the case where they're all different colors. Okay, so I looked at basically 3 different 5 different situations, right? But they may not all even be possible, right? But my idea is to see how many of any given case is possible, because then, for the most part, they would determine the other possible the other squares. So, is it possible to have this scenario where we would have the two down here be the same color? So it turns out that that is in fact possible. You may want to say to yourself, well, could those be green? The answer is no, because if you make these green, you still have 3 blues. So at some point, some 2 blues are going to have to be next to each other. So this would not be possible. So then obviously those two need to be blue, right? So we will make the case where these two are blue, right? And then remember how we said that this has to be a different color. Now, actually, I'm going to show you why. Oh, no, never mind. Okay. So now, well, you know what? Let's start with the case where they're all blue, just to get that out of the way. So is it possible to have it that those 3 are all blue? Yes, because then all you have to do is kind of make it symmetric over here, like put a green over here, and then make these 2 both red, and then there's a case, right? So we just found one case of where this is possible. And by one case, I mean one particular pattern, and it's clear that that's the only possible way, right? You couldn't switch like maybe these 2 around, because then you'd have 2 reds next to each other. So we found one way, one pattern, because remember, the 3 times 2 takes care of the colors, but the 1 represents like this particular arrangement of like, pattern, right, of the colors. Now, what if that top right one was green? Is that possible? So I'm gonna erase this, right? Is it possible that the top right one is green? And the answer is yes, because what you can do is you can make, so obviously this one has to be red, right? There's no other possibility. Now you have a green and a blue, so the only way that's possible is if this one is green and then this one is blue, right? So that's another possible arrangement, which takes account this one. And we can clearly see that, like, by choosing this to be green, these 3 were forced. So there's only one possible way that that could be done, right? But then if you think about it, these 2 situations where it's bottom left and middle, and then top right and middle, they're just kind of like taking the whole board and kind of flipping it, right? Like basically flipping it around, like making this blue, making this green, and then just flipping. So it's like flipping it along this diagonal essentially would create another situation, which would just give you one of these. Does that make sense? So basically, like, take the whole board and just reflect it over this blue line that I drew, and that's another situation, right? So now we have to say, is it possible where this one up here is blue? Sorry. Is it possible that this one up here is blue? I cannot get the blue to work. And then let's say the middle one is the so what I'm thinking of is the case where this one and this one are the same, but this one's different. Well, that would have to be green. So is this possible? So the answer is no, because the only other possible place for the last green would be this one. And then we need one more blue, but no matter where we put that other blue, it's going to be next to another blue. So this situation is not possible, right? So then the only other thing to think about is this situation possible, where each ones along the diagonal are different colors? So obviously no, because where are you going to put the red, right? Which one of these can be red? None of them, because these are both red. So this situation's also 0. So how many different arrangements do we have when these 2 are the same color? We have 1, 2, 3. So far we have 3 times 2 times 3, or 18 possible boards that we've made so far, right? So up to this point, we now have 18 possible boards. All right, now I'm going to erase this, right? And now we're going to consider what about the case in which, and you know, you would have to convince yourself that I've covered all possibilities, right? Just, you know, if you really think about it, I've covered all possible, and you can see how systematic I'm being, right? Making sure that I'm not double counting and making sure that I'm not missing anything, right? Right? And then the other thing would be to consider, what about if those two are different? Well, obviously, for them to be different, this would have to be blue. But again, we have 3 possible choices for the top left color, right? Which, which I've just randomly chosen to be green. And then we have 2 other colors to put, but we can switch their positions. So I can put red at the left middle and blue at the top middle, or I can switch them. I could put blue here and I can put red here. So times 2 for the arrangement of the other 2 colors, right? And again, I'm going to look at the exact same cases. So I shouldn't have erased those, but I'm going to look at same bottom and then top different. I'm going to look at bottom different, same top. I'm going to look at top and bottom are same and the middle is different. I'm going to look at they're all the same. And I'm going to look at, sorry, I'm being really messy. And then I'm going to look at they're all different. Right? Because if you think about it, those are the only possible, like what other possibilities could there be, right? So, is it possible that these two are the same colors and this is a different color? Well, the only way that these can be the same colors is if they're both green, right? That's the only possible way, because it can't be red and it can't be blue because there's already a red and you'd have a red, or you'd have something adjacent to its same color, right? So now we have 2 reds, 2 blues. Can we fit them in? Yes. This would be forced to be a red, right? Which means this one would be forced to be a blue. And the reason I'm saying forced is because it tells us that there's only one possible arrangement. Forced to be red, right? And this one would be forced to be blue. So there's one possible situation in which you have the bottom 2 same and then the top left right, top right different. Which again, take the whole board and reflect it over the diagonal line. Right, take the whole board and reflect it. Sorry, it gets messed up at the bottom. Right, flip the whole thing around, and you're going to have another situation. So you have one of those as well. Right. So now we have to see: is it possible that they're all 3 the same? No, because what 3 could be the same? They can't all be green. You already used the green. You already used up 3 greens. They can't all. So think about it. You have one of each color already. So what 3 can you possibly put on a diagonal? You only have 2 of each of them left. So that case is not possible, right? So we can get rid of that. One of these. What about this and this are the same? They both have to be green. That's the only possible thing, right? Can't be red or blue. And then you have 2 reds, 2 blues. But then what are you going to put here? You can't put a red or a blue here. So this is not possible, right? What about if they're all different? Will that work? So for them to all be different, well, remember, this is forced to be a green. The middle one, right? The middle thing has to be green. So then therefore the top right is forced to be red, right? And then the bottom left is forced to be blue, right? And then the rest are going to get forced because this has to be red. This has to be blue. Oops, I used a different color of blue. This has to be blue, right? And then this has to be green. So, right? Meaning so there's one possible situation in which this diagonal is all different. So that's one more. So we have 3 choices for top left color, 2 choices for either red, blue, or blue, red, whatever colors, they can be switched. And then we have 1, 2, 3 different patterns, right? 1, 2, 3 different possible patterns. So 3. 3 times 2 times 3 is another 18. So we have 18 plus 18, 36. And we know that's the answer because it's the highest possible answer choice. There's no answer choice larger than that. So that means we've gotten everything. So our answer would be E, and we are done. That's it, right? So the key thing for 25 was to be systematic, right? And that can be a really fun problem. Like I really enjoy those types of problems. I think this one required a little too much casework for me, but it's still a pretty fun question. And probably not the hardest on the whole thing. I think there were much harder questions earlier. I think 17 was brutal. Right, 22 was hard because I don't know how to get the answer without using technology. But this was overall a very hard AMC 10, probably one of the hardest ones I've seen in a long time. So, right, I don't know who's actually watching this, but good luck. Thank you for participating, and we'll get results soon. And that's it. Have a good one.